from Monty Python, and now for something completely different. So what we're going to start looking at is, kind of backing up architecturally and looking at, in a sense, we've been looking at the assembly stuff from sort of a low-level view, but really it's kind of high level in the sense that we haven't really considered the actual hardware that would implement this stuff. Okay, so that's something completely different. All right, now in order to do this, we're going to use this program called Logisim, and you can download it from the web, from GitHub. Let me just show you where it is. And you can run it on your Pi or on your other computers. There's versions for both. So it's called Logisim Evolution. And then here's the GitHub page. And if you scroll down a little bit, you'll see downloads, and then it'll say, download in compiled form or platform-specific packages. So if you click there, then you'll get to the most recent version, and you're going to see, okay, Ajay, here's your version, the RPM. For the Pi, you want the Java version. Mac, obviously the DMG. Windows, you want the MSI, and then the other kind of Linux package, depending on which one you use. You use the deb instead of RPMs. Okay, well, there they are. And of course, there's also the source code and stuff there. So download that. But in order to run it on the Pi, it's a Java file, right? So if I go to desktop, then, or not desktop, download, sorry. Then I've got this, it's a jar file, wherever it is, okay? And so the way I run it is by running Java jar, and then what was the name of it? Am I blind? Logisim, there it is, okay? Like this, okay. Now, if you just do this, you're gonna get the following error. Okay, and that's because the version of OpenJDK, which is the Java runtime environment and stuff, that is installed on the Pis is version 11, and you need a newer version. The most recent one is version 17. So here's how you fix that. So sudo apt-get install JDK, is it JDK? Sorry, OpenJDK. OpenJDK 11, but you want 17. Hold on, let me double check that I've got the name right. I think this is it. Nope, dang it. That's not it. It's not OpenJDK 11. It's a more recent version. Damn it. I just did this on my other computer. All right, well, this is not going to work until we update it. So, shit. Okay, this isn't going to work. Why will it not let me open Java 17? All right, hang on one second. I just did this on my office one, but of course on my office computer, Pi, I have the, let's see if we can do it here. Okay, well, shit. It wasn't installed on here yet. It was the problem. Uh, oops. Well, so no, because if I do sudo apt install open JDK, see, version 11 is the most recent that it has, right? Which it's, oh, there we go. Okay. Debug demo doc JDK. Let's do just JRE. It should already be installed, right? Yeah. Yeah, okay. So on my Office Pi, I updated it to a newer version of the operating system, and that one I think can do 17. So, all right, I'll give you guys some instructions. Don't worry about it. Huh? Well, yeah, I mean, I can, but that's not going to do, oops, there it goes. Okay. That's not going to fix it, or at least I don't think it will. Okay, anyway, while that's running, let me switch over to my laptop and we'll just do it on that. And I'll send you guys some instructions for how to get this working on your Pis while that's running. Yeah, because what I did was upgrade to the distribution. So, okay. All right, so let me quit some stuff here so it's not bothering us. And then I want to do Logisim. And then because I had a problem on Tuesday or Friday with, okay, so Logisim, window capture, this one. Okay. I captured a blank screen on Friday for my CS101 class. It was great. Okay, so while that's doing its thing, let's switch over to this computer. Okay, and so here's what the program looks like, and it looked the same on the Pi. So, okay, what, we've done plenty of stuff where we've done logical operations with gate, like AND gates, OR gates, and so on, and all of those are here, right? So we've got an AND gate, we've got an OR gate, and we have a NOT gate. And if we've got those three, we can build all the other ones, but of course there's the XOR gate, the NAND gate, and the NOR gate there. And we've used some of these logical operations when we've been programming, maybe not necessarily all of them, but yeah, okay. So what I want to start with is sort of like, if we look inside, how would you actually implement any of these gates with transistors in a processor, okay? And the way that it's done nowadays anyway. So I'm going to put 2 transistors here, and then I'm going to modify one of them, and I'll explain what I'm doing in a second. Okay, so I'm going to put an LED here. Okay, just for sake of demonstration. Okay, and I'm going to wire this thing up here. Now, the one thing that I'm not necessarily worrying about from a real electronic standpoint is what resistances are and some of those little details, but I don't have to worry about all of that. Okay, so then I'm going to put my power here, and I'm going to put my ground over here, and I'm going to connect power to there and ground to here. And then I'm going to, so right now it's got these red lines. That means there's an error because I'm not done yet, basically, is the issue. And then I'm going to put a button, okay? And this button I'm going to connect to my 2 transistors, right? So it sort of controls both transistors. Now, there are 2 types of, well, there are lots and lots of different types of transistors, okay? The simplest one that you've probably used is called like a BJT transistor, and there's 2 flavors of them, NPNs and PNPs. Have you guys had to wire up bare transistors in robotics? Probably not, but okay. Those of you who took 101 with me, I know it's probably been a while, did we do the thing where we put transistors on a breadboard and you guys wired up an XOR gate? Right, is this sounding, or did I demonstrate at least building a few logic gates up at the front? Okay, so that sort of thing. Okay, great. But those types of transistors is not what's actually used, at least in modern microprocessor fabrication. What's used are what are called MOSFETs. MOSFET stands for metal oxide semiconductor field effect transistor. Okay, so yeah, so it's a nice mouthful. Use it at a party. You'll get all the people that, you know, whoever you're seeking at the party. And the way these things are constructed, I mean, we could strip down one more layer and look at like actually silicon fabrication. Um, and it's sort of voodoo, but also it's kind of like, well, so you guys all know that, you know, 3D printers exist, right? And a 3D printer works by depositing material and building something up from basically a flat plate. Well, okay, imagine that you could also carve away stuff with your 3D printer. So it could both add and subtract material. And there were lots of different types of material that you would add and subtract. Now with 3D printing, it's basically plastic of some sort, right? And the print head just heats that plastic up really hot so that it's basically liquid, or, you know, sort of really thick liquid, and then extrudes it out. And when it hits the surface, it cools down and solidifies, and then you get, you know, whatever shape. So microprocessor fabrication is somewhat similar in the sense that you're going to deposit material and then you're going to selectively remove parts of the material. And the way you selectively remove parts of it is you put down a layer of stuff, and then let's say you want to etch a pattern into it. Well, you take the pattern that you want to etch and you basically make like a paper cutout that has the pattern as holes and the complement of the pattern as the paper. And if you shine really, really high intensity UV light through this thing, then the light goes through certain parts and hits certain parts, and other parts of the material are in the shadow, right? And being exposed to this UV light or not exposed to it changes its chemical properties. So then you throw it in a bath of hydrofluoric acid, you know, just cause, right? That's lovely stuff. Which, by the way, hydrofluoric acid is very dangerous. What would happen if you were to touch some? Well, not quite. It would seep through your skin and dissolve your bones from the inside out. Yeah, it's nasty stuff. Um, yeah, basically. Yeah. You'd probably also be dying, but yeah. So, yeah, don't mess with that stuff. Okay, but anyway, if you do this in controlled environments, then it's, it's not that horrible. But you etch away certain parts of it, and then you redeposit a different kind of material that's in the etched things. And if you layer this up a couple of layers, you can build, circuits with it. And then if you put these things together enough, then you can do an entire microprocessor, which is essentially just crap tons of these transistors all arranged in a certain way in order to implement some sort of digital logic. Okay, but at the fundamental level, it all comes down to this. Okay, so we have two transistors here. Those are the little thingies, one above my mouse cursor, and then this other one that's got the little loop on it. And those are MOSFET transistors. Okay, so it's a different type of transistor, and they come in two flavors, NMOS and PMOS. NMOS is this one. PMOS, the same symbol, but it's got this little loop on it. Okay, and the way these things work is they're voltage controlled switches, essentially. Okay, now I'm sweeping under the rug like a semester's worth of physics here, but uh, y'all will forgive me, right? No? Okay, well. All right, so there's lots of physics here, and like I said, I'm kind of sweeping that under it. If you want to learn more, right, go ask Dr. Brown. But uh, basically, the way that they work, you can think of them in a primitive sense as just being switches, right? Just like the light switches in the room. The switch can either be on or it can be off. Okay, now that's not entirely true in actual electronics because when we say on, we mean high voltage, okay, where high is defined as whatever we're powering our thing with. In like an Arduino or a Raspberry Pi, it's like 3.3 or 5 volts. In modern processors like Intel stuff, it's like just over 1 volt, right? Okay, so whatever the voltage is, so we'll call, let's say 5 volts is our operating voltage. High voltage would be something in the range of like 4.7 and above, right? So basically close to 5. And low voltage, which will count as a 0, would be stuff close to, it may not be exactly 0 volts, but way down there. And then the stuff in the middle is sort of the no man's land that we hope that we never actually are in, because that's sort of weird. And but if we sort of treat and design things right so that we're basically always in a state of either basically high voltage or basically low voltage, then we've made a digital thing, right? Ones and zeros. Okay, so these switches, the light switches, can either be default on or default off. Okay, meaning if I don't touch the thing, is the switch closed or open? Okay, so light switches on the wall are maybe not a good example of this. Think more like, imagine you had like a spring-loaded switch, and the spring loading could either keep it so that the switch was pressed by default and you had to like pull it to unconnect it, or the other way, that the spring, was trying to push the switch open, meaning not conducting, and you would have to apply effort in order to close it. Okay, so those are the two, if you had spring-loaded switches, you could imagine those two different kinds. Um, and that's what NMOS and PMOS basically are, is that the NMOS is default open, meaning you have to exert effort, you have to deliberately close it, which would be like pressing the spring-loaded button, or the PMOS, which is like the one that's spring-loaded closed, and you'd have to exert effort to turn it off. Okay, does that make sense? Okay, so the color scheme here, dark gray is basically 0, and dark green is basically 0, light green is basically 1, okay? And we can treat it as that. And then my little LED will have sort of a bright state, which is what it's in now, and then a not bright state, which obviously would look darker. Okay, so this simple thing that I've wired up, I've got that little box is a button, okay? And the button is, right now, it's off. If I press the button, watch what happens to, and the way I press it is I change from the cursor tool to the little finger tool, and then I press it. Okay, so what happens? It turns off. Okay, so what's true about the output light based on the input button? Okay, so the light is default on, okay, because the button is default off. But if I press the button so that my input is on, what's the output? Okay, so what is this? Uh, well, okay, yeah. The spring thing, I'm thinking of those as being the individual transistors, but I put two of them together here. So if my input is a 0, what's my output? If my input is a 1, what's my output? What is that? That's a NOT gate. Okay, so this is how you build, or a way to build a NOT gate with these, with MOSFETs. It's not the only way, but this is a way. And this turns out to be the way in terms of modern fabrication. Okay, you'll notice that I really have two transistors here. Now, those of you who have taken electronics know that you actually could have gotten away with just one of them if I wired the circuit up differently. But I've deliberately done it this way, and notice that for every NMOS transistor, there's a PMOS transistor to go with it. Okay? And this is what's called a CMOS process, for complementary metal oxide semiconductors. The NMOS and the PMOS kind of play a complementary role in terms of the electrical properties, okay? And so the sort of design rule will be you put them in pairs. Every time you have an NMOS, you have a complementary PMOS and vice versa. Okay, and I think you guys will see what I mean here in a minute when we wire up a Nand gate. Okay, all right, so does that kind of at least make sense, right? There's an inverter, okay, or a NOT gate. Okay. Now I would draw this a little bit differently by hand, but that's okay. Let's see. I may have to reboot this thing. Let's just do that while it's doing its thing. Okay, so let me make a new new subcircuit. Oops, I can't name it that. Okay, and I'm going to do something sort of similar. Okay, I'm going to have power. I'm going to have ground. Okay, but this time I'm going to put in 4 transistors. So let me just get 4 of them in here, and then I'll wire them up and explain what I'm doing. Okay, so I want these to be N-type and N-type. Okay. Yes, which is part of the point of the complement part, right? So yeah, they come in pairs basically. Okay, so I need power to here, and then I'm going to connect this to there, and then I'm going to put an LED here, and then I need the button basically. Now for the button, I'm going to do something slightly different. I want 2 buttons, okay? And I'm going to think of, okay, button 1, I'll connect to the first transistor in each group. Oops. Sorry, this should be connected to power directly, and this should be connected to the output. And then, so button 1, I'll connect to each of the 2 transistors. transistors, and button 2, I'll connect to the other ones. Okay, and the reason I use this dip switch is because with the little finger tool, I can only press one thing at a time, and I obviously have two things to press here. Okay, so let's make a truth table out of this. If both of my switches are off, which is what they currently are, what's the output? On. Okay, so make a little grid on some paper, right? And there are 4 possible inputs, right? 0, 0, 0, 1, 1, 0, and 1, 1. Okay, and what I'm going to do then is flip and do all 4 possible combinations of my input switches, right? So I've got 0, 0. If I do 1, 0, what happens? Still on, okay? If I do 0, 1, what is it? Still on. And if I do 1, 1, what is it? Off. Okay, so write down that truth table and stare at it for a minute. Huh? Careful. Okay. All right, so which gate is this? This is a NAND gate. Okay. Right, so if I just write this up on the board, right, we have 0, 1, 0, 1. Then what we have here is a NAND gate, the symbol for which is that, right? Okay, flat back with a loop at the front, and the loop indicates sort of that it's the opposite. Okay, well, that's great. We can build a NAND gate. How would we build an AND? Because we've definitely used AND in our programming. Well, we could, or we could be smart and just put together the two things that we've already done. Because if I follow this with a NOT gate, what do I get? I get an AND gate. Okay, so we know how to build a NAND gate. We know how to build a NOT gate. So if we put the two together, could we build a AND gate? Yeah. Okay. All right, now, I want to concentrate on the transistors and how I arrange them here. So you'll notice there's 2 NMOS and 2 PMOS. They always come, every NMOS has a complementary PMOS and vice versa, okay? But also the way I wired these things is also complementary. How did I wire, so I've got the 2 NMOSs over here on the right. How did I wire those? Okay, so if I've got 2 things and I want to wire them, there's 2 options for how I wire them. What are those 2 options? They could either be in what or what? Come on, guys who did physics. Huh? Yeah, they can be in series or they can be in parallel. Okay, now this is the time of season actually where that distinction is really important. If you wire up all your Christmas lights in series and one of the bulbs burns out, what happens? The entire string of lights is off because the circuit's been broken. Okay, and then, huh? Yeah, okay, which is what they do to, manufacture so that it doesn't knock out the entire thing, but you're not wiring everything literally in parallel because that takes a lot more wire, right? So they do it in little segments. Okay. All right. If you wire all of your Christmas lights literally in parallel and one of them burns out, then what happens to the rest of them? Nothing. They're all fine, right? And then it makes it very obvious which one is burned out, and you can, replace it. So, although nowadays I think Has anybody bought Christmas lights this year or maybe last year? No, I mean, you guys are college students, right? Nowadays, they're pretty much all LEDs, and so they don't really burn out so much anymore because, but back in the day, they used to be little incandescent lights, which, you know, I don't know if you guys remember incandescent light bulbs. No? Yeah, they'd get really hot. It's like the most monumentally inefficient way of turning electricity into light. It was very good at turning electricity into heat, not so much into light. So anyway, um, okay. So I've wired my two NMOSs here in series. How have I wired the PMOSs? And I know it's a little bit of a rat's nest, but kind of stare at them for a minute. And the way you sort of answer this is how could you get from the voltage source, which is just underneath my mouse cursor, to the right side of either of the two PMOS transistors? I could theoretically go through either one independently. I don't have to go through both, right? That means they're wired in parallel. Okay, so every time I have a pair of NMOSs in series, I have a complementary set of PMOSs in parallel. And if I flipped this and had NMOSs in parallel, I'd put the PMOSs in series. Okay, so that's another sense in which I say complementary. Okay, because they're, you know, they're in sort of opposite arrangements. Now, what about if I flipped this and I put the two PMOSs in series and the two NMOSs in parallel? We'd get something different, right? What do you think we'd get if we did that? Yeah, these two are in series, right? Because to flow through them from here to here, you have to go through both of them, one after the other. Whereas on this side, if I want to go from here to here, I could go either through this transistor or I could go through that transistor. Huh? That's electrical. That's ask Dr. Brown. I'm just going to foist that off on the physicists. Okay. Okay. Trust me, I'm a doctor. Okay. So let me just take what I have here and I'm going to copy it all and I'm going to make a new subcircuit. I'm going to call this mystery. Okay. Now let me undo a few things. Oops. Okay. All right. So this time I'm going to put those in parallel, or sorry, in series, but these two I'll put in parallel. Okay. So you guys see how I changed it? I changed the series to parallel and the parallel to series. Yeah? Okay. So let's do the truth table. What are both inputs? Off. What's the output? Okay. So if I do one on and the other off, I get what? Off. If I do the other off and this one on, I get off. And if they're both on, I get off. So when is this, what is the truth table for this one? Okay, what is that truth table? This is a NOR gate, the opposite of OR, right? Okay, so now that kind of makes sense because I switched my complementary structure and and OR are complementary objects because, well, how many of you guys are in Math 108 or have taken Math 108? I'll take De Morgan's laws for 500, Alex. Okay. Yeah. That's basically what's going on here, right, is De Morgan's laws. Okay, and so now I have a NOR gate. Well, what about if I want a regular OR gate? With a, yeah, an inverter or a NOT gate, okay? So in the same way that I had a NAND gate and I had a NOT gate, and I could put those together to make a regular AND gate, could I take a NOR gate and a NOT gate and make it a regular OR gate? Yeah, Cole, you look befuddled.
Are you saying that to get from NAND to NOR, you put a NOT gate?
No. To get from NAND to AND, you put a NOT gate. Right? So if I take this circuit and instead of that light, I put a NOT gate there and a new light, then I would have the opposite of what I've got, which would be regular OR instead of NOR, right? Okay, does that make sense? Well, there's 6 out of the 7 basic ones, because we've got, or maybe, sorry, 5 out of the 7. We've got AND OR, NAND NOR, and NOT, and then what are the only 2 that are left? XOR and NXOR, and we can build those with combinations of these things. Okay, all right, so does that kind of make sense, this complementary structure? Yeah, okay. And the brilliance is by having the complementary structure, because there's good electrical reasons for that, in terms of where current's flowing and heat dissipation and things like that. Okay, now they weren't originally like this in processor technology. So in fact, early processors, the Intel 4004, used only PMOSs, and the Zlog Z80 used only NMOSs. And the reason was fabrication techniques have not gotten to the point where you could build both of them simultaneously to have similar speed performance and all of that. One of them was faster than the other, and it took time in order for the fabrication technology to make it so that both were equally valid. Okay. All right, so a processor really is just going to be crap tons of these things put together in very logical ways. Okay, so if we zoom out a bit, we can think of this entire contraption that I made as really being this symbol, okay? Because I've got 2 inputs and 1 output, right? And similarly, the other one, I can think of replacing with, with that symbol, right? Okay, and so think we're going to sort of zoom out 1 layer and only worry about things in terms of the individual gate symbols and not the transistors that are sort of hidden inside, right? So we can just zoom out 1 layer, and we could zoom out more layers or zoom in more layers, right, down to the point of like actual like atoms and stuff. Okay, so good? Okay, so if we start to put these things together in interesting ways, okay, now let me write this on the board, but let's say that I wanted to do addition. Okay, I want to design a circuit that's going to handle addition for me. Well, in order to demonstrate that, so let me actually use the other board there. Let's just think about, how do I add a single bit to a single bit, right? Now, there are 4 possible combinations of what the 2 bits I'm adding are, right? They could both be 0, they could both be 1, or they could be 1 and the other, right? Okay, so let's write all 4 possibilities down. Okay. What are the results of these things? What's the sum here? What's the sum here? What's the sum here? What's the sum here? Ah, I heard the magic word. What was the magic word? Carry. there's really two outputs that I need to keep track of. The sum and possibly a carry. What are the carries for all four of these? Yeah, okay. So I need to build a circuit that has two inputs and two outputs. One for the sum, one for the carry. Yeah? Okay, stare very closely at the sum results and the carry results. And for the sum, what circuit or what gate do I need? Huh? I need an XOR gate. Oops. Okay, because the output of the sum allows one input or the other to be on, but not both. Okay, so right, the difference between OR and exclusive OR is what? You can't have both, right? So when I'm home at Christmas, well, maybe not at Christmas would this be a problem, but if my mom asks me, do you want chocolate or vanilla ice cream for dessert? And I say I want both, what's probably going to happen? I'm going to get smacked and I won't get either. Okay. So exclusive OR, you can get one or the other, but not both. Regular OR, you could have both. And of course, in English, when we use the word OR, we sometimes use it in both senses, right? Do you want chocolate or vanilla ice cream for dessert? My mother's intent is no, I do not get to have both. Okay. Yeah. All right. So the sum I can implement with just an XOR gate. What about the carry? Which gate do I need to generate the carry? Yeah, I need an AND gate. Oops. All right, which is just that. Okay. All right, so let's build it. Okay, so what I'm going to do here is I'm going to start using these little guys as my inputs for reasons that'll become clear later. Okay, and which two gates do I need? I need an XOR for the sum, and I need an AND for the carry. So both inputs need to be wired to both transistors. I mean, both gates, excuse me. And you, yeah, and you, yeah. And then I'll put outputs here, and I'll put an output here, and I'll connect this guy here. And then I'm going to name my outputs. This guy, I'm going to call the sum. And this guy, I'm going to call, oops, the carry. Okay? Okay, so this circuit is what's called a half adder. Okay, so instead of mystery 2, I'm going to, I don't think I can rename it, so let's do, I thought I could rename it. I guess not. Oh well. All right, so this thing is a half adder. Why might I call it a half adder? Seems like we've added everything we need to worry about. Ah, that's the full adder. Okay, so this is perfectly great for doing just regular addition of the last bit of a number. Okay, but if I add multi-digit numbers or multi-bit numbers, what's the problem for the second and beyond bits? There could have been a carry from the previous bit, right? So if I add, oh, damn it, chalk has a tendency to migrate. If I add two bit numbers, and I'm just going to make it up here and say, let's add 1, 0, and 1, 1, or let's say we add this, right? Well, what do I do in the far right position? 1 and 1 is 0 and carry. But now in this position, what do I have to do? I have to do the same thing, but I have to do more than that. Okay, not only do I need to add the 1 and the 0 like usual, but what else do I have to worry about? The carry that came in. Okay, so now this version of the addition circuit needs to have 3 inputs. The 2 input bits and the carry from the previous stage. Okay, so the circuit that we've got on the screen right now ain't gonna do it. We need more than that. Okay, and that circuit is what we'll call a full adder because it takes 3 inputs and produces 2 outputs. 2 bits in plus a carry in, and some out and another possible carry out, right? Because like in this case, for the example I picked, 1 and 0 with the 1 carry from before, I'm going to get a sum of 0, but I will still generate a new carry that would go to the next position. Yeah? Okay, so great. And that circuit is called a full adder. Okay, and for sake of time, I'll just make it real quick. Okay, so what do we have here? We have 3 inputs, right? And I'm going to call this NA, NB, and NC, okay? And the way I'm thinking of this is NA and NB are my 2 bits that I'm adding, and NC is the possible carry from the previous bit position, okay? Okay, now, I'm still going to need basically a half adder, but I need to add stuff to it, okay? So what did we need in our half adder? We needed an XOR gate, and we needed an AND gate, okay? And let me just look it up for the sake of speed. Okay, so, all right, so I need 2 AND gates. I need 2 XOR gates. And let me just arrange this in a semi-logical fashion. Okay, so I'll put the XOR gates here, one of them there, and one of them here. And then I'm going to have my AND gate there, and my AND gate here, and then I'll also have an OR gate there. Okay, let me wire it all up, and then we'll talk about it. Okay, and then I need to do A to here, this to here, B to, well, here, let me just scoot B up a little bit. B to here, and then I'll do A to the bottom and, B to this and then I'll put this guy goes up to here and here, and this comes to there. Okay, and then I need to have 2 outputs, so I'll have my sum and my carry. Okay, so right now, what are all 3 of my inputs? They're all zeros, okay? So what should I generate as my sum and my carry in that case? Well, clearly all zeros, right? Okay, so let's take it and change it to the situation I had up on the board, which was one of the inputs was a 1, the other was a 0, and I had a previous carry. Okay, what's the sum in that case? A 0 with a carry. Okay, what about if all 3 of them were 1s? What should I get? one sum and one carry. Okay, and let's just double check that that works. Okay, it does, right? We get one sum and one carry. Okay, so this thing is our full adder. Okay, so essentially the top part is determining the sum, and the bottom part is determining the carry. Okay, and so, and if you sort of think about it for a minute, under what conditions is the sum a 1? Well, if one input is a 0 or the other input is a 0, that first XOR gate would give a 1. Okay, and then if the carry is a 0 and the sum is a 1, then we get a sum of 1, right? But we could also have a sum of 1 if we had two zeros and a carry, right? So there's two kind of possibilities there. And then the carry part of this is a little bit more complicated because, well, I've got three inputs, right? So, okay, so there's our full adder. Okay, does that kind of make sense? All right, now let me go back to my half adder and let me, which I think I called this guy. All right, and let me change the name here for my inputs to NA and NB. Okay, and this is where I think you guys will really like this program. Okay, because what I'm going to do is I'm going to take mystery 2, which is a half adder, and a full adder, and I'm going to put them together. Okay, so mystery 2, that box, think of it, I couldn't rename it, but that's the half adder that I built, right? And the full adder is this other thing that I built. So if I were to double click on these things, that would zoom me in to what those individual components are. But now I'm zooming out one more layer and saying, okay, what happens? I've got a full adder, I've got a half adder. How do I put those together to make a larger addition circuit? Does that kind of make sense? Okay, so how would I put these things together to make a larger addition circuit? Well, I need to have some inputs, right? But how many bits should my inputs be given what I've got so far? Yeah, well, hold on. I need 2 bits for both of these. Let me scoot this stuff over a little bit. Okay, because if I put these two together, I'll be able to add 2-bit numbers to 2-bit numbers. Okay, now, what should go into the half adder? Which bits from which numbers? Well, okay, if I want to add two 2-bit numbers together, then the one on the far right, the least significant bit, goes to the half adder. Okay, all right. So I need to take the far right bit from each of these two numbers and connect those to the NA and NB of this guy. But these are two guys that are 2-bit numbers. So I need to split that thing into its constituent bits. And the way that I do that is with a thing called a splitter. I know that's real creative, right? Okay, so I'm going to connect this, and bit 0 is going to become the input here, and bit 0 is going to become the input there. And then bit 1 will become the input for the other two. Okay, all right, now I get a sum, and my sum is going to be an output. How many bits? How about 2 bits? Okay, and I might also generate a final carry, right? Right? So how do I put the sum together? Because I've really got 2 sums. Well, what's the top sum? That's the far right bit sum. And the bottom sum is the second bit. So I need to put those two bits back together. And how do you think I might do that, Cole? A combiner, aka a splitter in reverse. Okay, so I'm going to take my splitter and I'm going to flip it around. Huh? Yeah. All right, and I'm going to put bit 0 here and bit 1 here. No, which bit position it is. So our convention, right, is the 0th bit is the far right bit, and the first bit is the second bit, right? Because we start counting at 0. Now, in this case, then, if I had more bits, like I wanted a 64-bit of this, then it would be 0 through 63, right? And that makes sense, right? Okay, so what about the carry? Where does the carry come from? Well, it comes from here, but I'm not quite finished wiring this. What am I missing? The other carry. And where does this go? You come around here, right? Okay, so what I have here, boys, is a 2-bit addition circuit. Huh? Mm. All right, let's build a 64-bit one.
I don't want to have any responsibility for that.
Well, okay, but seriously, how hard is it, right? If I wanted a 64-bit addition unit, I just need 63 of these and one of those. Huh? Well, if only there were keystrokes that you could do to copy paste stuff real fast. Wouldn't that be great? Right, but essentially I just need to copy and paste my full adder a whole bunch of times, add in bigger splitters and whatnot, and yeah, I could make an 8-bit unit. Okay, and if we think about the ARM addition circuit, let's actually go a step further, because how many different add instructions were there on the ARM for integer addition? There were 4. Right? Okay, well, the C stands for carry, and remember we had a carry flag. So if I were to put 64 of these things together, what would happen to the 64th carry? I would use that to set the flag to 1 or 0 if I was doing one of the instructions that had an S at the end of it. Otherwise, I would ignore the flag. Okay, and similarly, what's the add C and add CS? What do they do? In addition to just doing adding, they also take into account the result of the carry flag, right? So the ARM addition unit is actually going to be all full adders, okay? Because the carry flag, if we were to use it, we would need to come in. Okay, does that make sense? None of them. Okay, because we have a carry flag that we might want to use. Okay, now think about it this way. We've got 4 different addition instructions there. Should we build 4 different addition units in our circuit or like our processor? No, that's a monumentally bad idea. Why build 4 of them when you could build 1 and use it 4 different ways? Right? So that answers that question, Farden. There's only 1 addition unit. Okay, so in a modern computer, there would not ever be a half adder in the addition circuit. Okay, now the other thing that we have to kind of talk about is, let's say that I took and put 64 of these full adders in a chain, okay, and wired them all up. And I take 2 64-bit numbers and I put them into my 2 inputs, okay? Am I going to get a 64-bit output and a possible carry bit? Sure. How long will that take? Will it? Okay. So when I flip these bits, how fast does the answer pop out the other end? Okay, well, it kind of asked the question, how fast are the transistors and stuff in my circuits? Is it instantaneous? Can it be instantaneous? No, nothing can be instantaneous. Is it damn near instantaneous? Yeah, okay. But see, here's the problem. Damn near instantaneous times 64 may not be very instantaneous. Okay, and so what we call this is gate delay. Okay, so the gates cannot switch instantly, right? Now, the time scale that they're operating on is very, very, very small. Okay, we're talking like micro or even picoseconds. Okay, huh? Yeah, okay, which is really damn fast. Okay, but how fast is the processor in your desktop computer, or heck, even the Raspberry Pi operating at? Yeah, it's in hertz, but it's a few more than that. You know, like on the gigahertz range, right? The turbo boost on the Raspberry Pi processor is 1.5 gigahertz, or possibly actually 1.8 gigahertz if it's a newer revision. Okay, or on modern like Intel and AMD stuff, the turbo boosts are at like, you know, 4, damn near 5 gigahertz. Okay, well, if your gate delay is from 64 of these things and you're operating your processor at 5 gigahertz, that gate delay may actually cause you a problem. Okay, so this is sort of the most naive way to build an addition circuit. There are more exotic ways that try to speed things up. Okay, but in terms of the structure here, does it make sense how this is supposed to work? And anything else we do is just trying to speed it up by doing sort of parts of the computations in parallel, if we could. Okay, and in reality, that's of course how a modern addition circuit is going to work. If I wanted to build like a little 8-bit computer, this would probably be fine. Okay, just 8 of these things, 8 full adders. All right, well, if we can build addition units, how could we build subtraction units? Kind of similar idea. Well, if I can do subtraction and addition, could I do bit shifting and bit rotation and logical operations and, yeah? Okay, and if we were to zoom out one more layer, what we would be building is called an ALU, Arithmetic and Logic Unit. And it would have within it the addition component, a subtraction component, a logical OR component, a logical AND component, a bit shifting or rotating component, right? So it would have all of these different pieces inside of it. And guess what y'all's assignment's going to be with this? Yeah, to build an ALU. Okay, and for sake of simplicity, we'll keep it as an 8-bit unit. Okay, because what's really the difference between 8-bit and 64-bit? Well, yes, 56 bits. Thank you, Cole. Right? How illuminating. Okay, but point being, it's just more of the same stuff when you do it with 64-bit. Okay, so for low clock speeds, this thing would be fine. Okay, because the gate delay is not going to add up all that much. All right. So speaking of clock speeds, though, all of the circuits that we've wired up so far don't have anything whatsoever to do with the clock. Okay, we need to talk about how that gets into it. Okay, and this gets into how do you actually store data and other stuff. Okay, so let me go back to a new thing. Okay, so there are a lot of other, you've got your gates, okay, that we had there. Now, there are actually built-in things for addition, right? So we've got a built-in thing that would do circuit that would do addition or subtraction and so on, okay? But you guys essentially are going to build those components. Now, if I wanted to be really evil, I could make you guys build one of those, right? Do like a floating point addition circuit. Wouldn't that be fun? No? You sure? Yeah. Okay. Right. Okay. So there's a whole bunch of these things, and yeah, they're built in. We could use those, but you guys are going to build them from scratch. Okay. Now, what I want to get to then are, not TTL. They've added a lot of stuff here. Memory. Okay. Okay. There are these things called flip-flops, and you can build them out of some of the different gates. All right, and let me just throw in here a clock signal, and I'm also going to throw in, actually, I'll throw in this kind of input. Okay, and then I'm also going to throw in light just so you can see the output for sake of demonstration. Okay, and I'll throw in another light on this other output. So this looped output at the bottom is just always the opposite of the top output because maybe you need it negated. Okay. All right. So I'm going to take this guy, and this little symbol, that squiggle, is a clock signal. All right. Now, what a clock signal would look like if you had an oscilloscope is it would basically be a square wave. Okay. Is it really actually going to be a square wave if you are doing this electrically? What's it probably going to be? Right? And so it's not instantaneous that it jumps up or down, right? There's a very, very slight transition period. And obviously you want that as small as possible. Okay. But for our purposes, we can treat it as if it's a perfect square wave. Okay. And so if I go here to simulate, I'm going to change the auto tick frequency to 1 hertz. Okay. And I'm going to turn on auto click. Okay, and so notice, what is my clock signal doing here? Off and on at a frequency of 1 hertz. So 1 second on, 1 second off. Okay, now obviously, how fast does a modern processor work? Trillions of times faster than this, right? Because it's at gigahertz speed, and here I'm working at a single hertz. Billions. Whatever. Lots more. I'm not a mathematician or anything. Right? Okay, so, right? All right, now, watch what happens to the output if I flip the input to a 1. When did the switch happen? The instant that the clock went from off to on. Okay, that's called the rising edge, namely this part. Okay, so let me demonstrate this again. All right, so let me turn this off. Right, you saw it. So let me actually turn down the frequency. Okay, so it's going to take a 1/4 second. Okay, so I just turned the data input on, and it's only right when the rising edge occurs that the data stored in this thing switches. Why does it stay on? Okay, it stays on right now because I've left this thing on. Okay, so watch what happens if I turn this off. Okay, what happened? Upon the next rising edge, it switched back to 0 because my input is 0. Okay, so this is called a D flip-flop or a D latch. It latches what the input is the instant that the clock goes to a rising edge. And it preserves that thing until there's a different input on the next rising edge. Okay, now I'm going to add one thing to this. Okay, and what I'm going to do is I'm going to delete you, I'm going to add an AND gate. Oops, damn it. Yeah. Okay, and I'm going to connect him to there, and I'm going to make a second input, which I'm going to call write enable. Okay, and then I'm going to connect that here, and then I'm going to connect him to my clock pin, and then I'll call this, say, input. Oh, I can't call it input. Okay. All right, so now let's say that I have a 1. Okay, and let me change the frequency so that it's for sake of time. Okay, 1 second, 1 second. All right, my input is on. My flip-flop isn't changing. Why not? Yeah, because look what I've got. I've connected the clock input, which is that little triangle. I've connected the clock and another bit to write, which I've called write enable, to an AND gate. So when is this input here going to be on? Only when both the clock is on a rising edge and the write enable is on, okay? So if I turn on the write enable, right, it latches, and if I turn off the write enable and change the input, does the latched value change? No, because I've used this bit to control whether or not I'm going to put data into this thing or not. Okay? Does that kind of make sense? Okay, so, yeah, so this thing that I've got is storing basically 1 bit of data. How would I store 64 bits of data? I'd put 64 of these things together, and if I grouped them, I would call that, you know, maybe a register or something. Okay, but again, I'm building individual little things and zooming to different layers to sort of say, well, how are each of these little pieces going to work? Okay, so this is how we build memory, both RAM and registers, or a way to build them. Okay, so if we can do that, and we can do arithmetic and logic stuff, we're starting to actually have the pieces that we could use to put together an entire computer. Okay, not completely, but getting there. Okay, all right, I've probably gone a little over, so we should quit. All right, I will send you instructions for how to get this working on your Pi later, because it will be a little complicated. Sorry, so see you later.